Welcome back to the Computer Science 144 video lectures. So in the past couple of weeks, we have discussed the performance of algorithms. Now from this week onwards, well actually we've started last week with that, we are looking at fancier algorithms. So in other words, we want to design algorithms that are faster and that will be able to solve large and big problems. Remember that we've said that sometimes just buying a new computer will not be enough to solve a new problem, and hence we should try to build algorithms that are faster. We have discussed in the previous weeks then ways to measure performance of algorithms. In other words, we have devised a set of methods. They are empirical methods, they are also mathematical methods that allows us to actually estimate the performance of an algorithm. In other words, we can have a hypothesis of the running time of an algorithm, and from that hypothesis we can go and make measurements, and we can refine the hypothesis, and we can predict the running time of new input if we give new input to our algorithms. Now we will use the same kind of methodology when we analyze the algorithms this week. So the approach is we will discuss a problem. From this problem we will usually have a so-called brute force algorithm. The brute force algorithm is the straightforward, the most simple algorithm, and then we will see that this algorithm will not be fast enough. So we will have a running time analysis of it, either with an empirical method, or otherwise we will do it with some form of a mathematical estimate. In other words, we count the frequency of the instructions that takes place, and from that we will then design a new algorithm that will allow us to do the calculations that we want to do. So the topic that we discussed then this week is sorting and searching. Now, sorting and searching are of the most fundamental algorithms that we find in computer science. You use them almost every day of your life. Not almost every day of your life. If you use a computer, you will use sorting and searching every day of your life. They are just everywhere. From your cell phone, where you want to see the contacts in your contacts book in the correct order, where you maybe type something in and then you want to quickly find a message or an email, where you would perform some searching. They are everywhere. You will also find them in Google when you do searches. We will not really do a Google search, but the idea of searching, finding information that you've had, they are just around us, and we're not even aware at this point that we use those kind of algorithms. We have in fact discussed some of the work in the previous lectures, so in a sense today's lecture is kind of a revision lecture. But as always, it's good to do a bit of revision, and we will add a bit of extra detail as we go along. Then the second lecture that we will have this week on sorting algorithms, there we will start with new work. So the first problem that we want to solve is the searching problem. So may I remind you that the searching problem is that we start with a list, an array for that matter, of entries, so with values in it. You can think of it as a list of numbers, an array of numbers, and then I ask you whether a certain number is in that array. Then you would return the index where that number is when you find this number, and if you don't find this number, you would return -1 or some other arbitrary value that indicates that you did not find the value in the array. So here on the screen I have indeed a implementation of a search algorithm, and that's a so-called sequential search. You can think of it as the most naive algorithm. In other words, it's also the brute force algorithm. So what's going on here? So let's see, we have in this case an array of strings, and then we have the key. So that is the item that we try to find within this array A. And so n is the length of the array, and then we go through each element in the array. So we start with the first element, and we ask the question, are you the key that I'm looking for? Are you? And if that is not the case, then I proceed to the next one, I do the next one, and so forth. And then one or two things will happen. I will either find a key where this element is, so then I would return the index I. Otherwise, I will go through towards the end of the array, and then I would return -1, signaling that I did not find the key in this array. So let's make a little client program that will use this array. So here we have a so-called exception list filter. So what do? Is I have a file, say test.txt. They contain a list of words, or in this case they are email addresses. Then I have a whitelist. The whitelist contains a number of entries that I proceed as my that I want to whitelist, and then if I run this program, it will output these names that are not in the whitelist but are actually in the test.txt. So you could think of it as a way for indeed email programs to do whitelisting. So these are the people you trust in the whitelist. These are all the email addresses that you receive emails from, and then this would be the people that's not in your whitelist, and then hopefully you will decide maybe to call this spam. That would be maybe a bit unfair, but you could flag this as a special case. Other things you could do, for example, is network connections to unapproved websites. So this could be all the websites you enter. You could think that you make a whitelist of websites that you can visit, and then here is a list of things that's not in the whitelist, but that we have visited. Another example where we can apply this is, for example, when the whitelist is a dictionary of words, and then test would be your document, and then this exception would be all the words that is not in the dictionary. So in other words, that would be the misspelled words. So it's sort of a way of doing spell checking as well. So let's look at the code here. So we read in the document the whitelist, and then we go through all the words and we just find them. So we look through all the words in our string that is this word in the whitelist? If not, well, then I print it out. So it's a fairly straightforward client program to use our searching algorithm. Now let's look at the running time of this algorithm. While this should be easy to see that, well, in the very worst case, you would have to go through all the elements in the array to find the element that you're looking for. So that would be that's order n time that you would do, since you have to do all the elements in the array. If you think of it more on average, then you would say you would have to go halfway through the list to find what you're looking for. So that would be n over 2. But n over 2, if you remember correctly, that is just also an order n times. So in other words, this sequential search is a linear time algorithm. So that brings us then to the question, if you have a credit card company that needs to whitelist 10 million customer account numbers, processing 10,000 transactions per second, what kind of computer do you need if you want to do sequential search? And even given the speed of our computers today, you would need a supercomputer or a Google server farm, or for that matter any other company who provides cloud computing server farm, to be able to handle this. So in other words, this is clearly not the best kind of thing that we should do in these circumstances. So let's see if we can do slightly better. And this is then where we will do binary search. So binary search is an idea of doing the searching algorithm much faster. Now the binary search algorithm is in a sense based on our intuition that we use. I mean, we've been using the binary search algorithm for quite a while. I don't know how many of you are still aware of the concept of a telephone directory. So for those of you who have never seen one, I believe you have seen one. This is this big yellow book or maybe they have some other colors as well. And then you would go and find a number in the telephone book of the person that you're looking for. Now, the linear option would be starting on page 1 and go through all the names one by one until you find the actual person that you're looking for. The binary search equivalent would be that you actually open the telephone directory and look at the first page and see there the page that you open where you are at this moment, and then based on that you find your place around in the book until you find the right one. Basically page through the book until you get the right place. Another way of doing that is of course with a standard dictionary. Perhaps you use dictionary.com or some online servers, but if you still use the old dictionaries, that's the book that you buy in the bookstore. Again, if you want to find the word, you can go sequentially, starting at A to the letter Z, and somewhere you will find the word. But if you want to find maybe the word predicament, then you could open the dictionary at some random place. It's not important where. You would see I'm maybe on the letter Q or whatever, and if you see Q, then you know you should go a bit to the left, and then you fiddle around until you find the right way. And that's the spirit or the idea of the binary search algorithm. Another way of looking at it is this 20 questions game. So the 20 questions game is that you think of a number, and then you try to find the number that the person is thinking about by just asking questions whether this number is bigger or larger than another number. Now let's just play this to put this in more perspective. So of course those who know me know immediately of what number I will be thinking. So I have there the program, and then I have to specify this is the number, the largest number I can take. So in other words, I can, in this case, well, it's the power 2 to the power of 6 is then the largest number I can take. You will see now. So it will ask me, well, 2 to the power of 6 minus 1, which is 63. So it will ask me, think of a number between 0 and 63. And now I'm thinking of my number. So is this number less than 32? No, it's not. So I can say false. Is it less than 48? Yes, it is less than 48. Is this less than 40? No, it's not. Is it less than 44? Yes, it's less than 44. Is it less than 42? No, it's definitely not less than 42. Is it less than 43? Yes, it is less than 43. And then the number is 42. And of course, I have thought of the number 42. So let's look at the implementation of this program and see what's going on there. So in this program, of course, this is just code that asks the n value that I've typed in, and then this is the bounds of the number that I can think of between n and to the power of n, and then I have this search method that tries to find the number that I'm guessing. Now, basically what it does is it asks a series of questions, and then if it is less than and then I halve the interval every time I ask this question. So if I go back to my slides, it's easier to understand here. So let's assume this person think of the number 67. Then I would say, is it less than 128? Well, then you knew it's less than 64, sorry. Then you knew the number should be between this one and 128. And then I ask, is it less than halfway between these two? Now, if it's less than halfway between the two, then I know it must be there. Then I ask, is it less than halfway between these two? And then the answer is no, so then I know it must be in this interval. So every time when I do this, I actually halve the interval, so the searching size. So that is just another, that's the graphical depiction, and there is the code to find this. So I halve the interval, and then based on that, I find where the number is. So let's make some running time analysis of this little program that I have over here. So let Tn be the number of questions. So Tn is number of questions. And we know, of course, that n is a power of 2, and n is equal to 2 to the power of n. We know that. Okay, so what we're trying to find out now is how many questions, how many questions we ask to get to the answer that we're finding. So t to the number tn is the number of questions. So we know that tn is equal to 2n over 2 plus 1. So why is that the case? Well, once I've halved the interval that I'm working with, then it means I've not added another question, I've asked another question. So whatever questions I've asked until that point, if I have halved it, then I add another one. And from the other equation that we have is we know that this is then equivalent to 2 to the power of n is equal to 2 to the power of 2n minus 1 plus 1. And now let's just apply this sequence to itself. So this is of course equal to 2 to the power of n minus 2 plus 2. And I can of course write it out another time, 2 to the power of n minus 3 plus 3. I'm just applying this over and over again by taking out another question and half the interval. So I can of course do that many times until I get to something like t to the 1. So I can do this all the way until 1 plus n minus 1. And of course we know that this should be 1, since if if it's 1, then we've just asked one question. 1 minus 1 is 0. So this is equal to n. So in other words, we have 2 to the n is equal to n. But now we can we know that n is equal to 2 to the power of n. So in other words, 2n is equal to the logarithm of n. So in other words, the number of questions that I have to ask is equal to the logarithm in base 2, of course, of this n, this interval size I'm using. So therefore we also have then immediately a running time estimate of this algorithm, since this algorithm will basically stop when we reach 1 over there, when the interval size is 1, and in a sense this is all the way until this point where the interval is 1. We know that that answer is log n. So I can say that the running time of this algorithm is log n times, given this n that we have, the interval size. It's kind of a nice algorithm to think that you can actually guess a number, any number, and then I would get in log n times, which is a rather small number compared to this n, the actual number that you were guessing. So this is of course also a justification for the binary search algorithm that I will discuss now in more detail. So let's go back to our slides, which will not open at this point. Okay, there it is. So the binary search algorithm is essentially the same thing that I've done now. In fact, this algorithm that I've just implemented is also a binary search algorithm, but now we're just finding an element, and so we have to make sure that we actually find the actual index that we're looking for. And of course, the examples, I've mentioned that at the beginning of the lesson, they are everywhere and we use them all over the place. So credit card numbers, book indexes, I mean these are for online things, but that's also how you would find it if you just use a book. So I have here a demo of how you would do binary search again. And so here the aim is to find the number 33 in this array of numbers. So I have the low index and the high index over there, and we're trying to find 33. So what we do is we find the middle, and then we ask the question, is 33 in this larger than the middle key, or is it less than that? And so no, it's not. So that means we can move the higher point down, since we know then this number should be somewhere there. Find the middle point again. We ask the question, is it in this part or in that part? Of course it's not in that part, so we have it over there. Then we ask the question, is it in this part or that part? If you have the middle, of course it's now not in that part, it's in this part. And then there we find the 33. So it's a fairly easy way of finding it. Note, however, how we also halve the interval always that we're trying to do. So we have it there, we halve it by not searching over there, and then we calculate the middle and we throw away that, and then we just work with that thing. So that's sort of the theme of this kind of algorithms, that we halve the search sites every time. So let's look at an implementation of this algorithm, and for some strange reason it's not displaying at all on this. Let's see if I can find a way around this. Okay, let's see, maybe that's I can show it like that. So since it's not displaying at the moment, let's see. I'll just make it slightly smaller, 100. Okay, so hopefully you can see it. Otherwise the slides are available as you watch this video, so you can just look on the slides to go with me through the code. So this is exactly the same as the Norman algorithm. We have here that if the high key is less than the lower key, well, then we didn't find it, so we return -1. And then we calculate this line over there, which is the middle key, and then we compare it, and if it's greater than where we want to be, then we search in the other half. Otherwise we search, we move the lower key up and we search in the upper half, and the alternative, if it's not greater than or equal, then it returns middle. Remember, I've discussed this algorithm within the context of interface inheritance, and you can see it over here as well. So I use the function there, compare to, and compare to over there is of course a function that I can call on a string class. This has then this description that it will return less than 0, 0, or greater than 0, depending on whether the elements that you compare is less than, greater, or equal to. I might have the order now incorrect. So any class can implement this compare to interface. So in fact, the search algorithm will work for anything that implements the compare to interface. So that's one thing I want to notice. The other thing that you should notice is that this is implemented in the arrays.binary search. If you look in this Java class, arrays, java.util.arrays, you will find an implementation of binary search over there. Then I urge you also to look at this implementation very carefully. I've done this now, and I went through it pretty fast by going through the demo that I've shown, through the 20 questions that I've shown you, and then I have also discussed this now quickly by going through this. And it seems rather trivial to write down this algorithm. However, in an experiment that John Bentley did a while ago, not a while ago, a long time ago, he asked about 50 professional programmers to implement the binary search algorithm in the language of their choice. So they could pick C, Java, assembly, for crying in a bucket, or whatever they want to use to implement this algorithm. And only 10% of them got the implementation right. So I think it's Professor Donald Knuth who made the comment, it's easy, but it's in the detail. So the devil is in the detail. So it's a simple algorithm, but make sure that you understand the little intricacies of this algorithm. One example, for example, is this line over there that's calculating the middle point. You could, of course, just calculate it otherwise and say high plus low over 2, and that would give you the middle point. But if you do it that way in Java, you would get an integer overflow. And in fact, in the Java library, system library until Java 1.5, that was a bug that was hidden there, and then someone shown that the binary search algorithm of Java actually has a bug in it due to this problem that you would get for very large arrays. You would get overflow. Remember that an array has a certain size, so high plus low over 2. If this is a very big number, this is a very big number, then this result of it might be much bigger than what the int can handle, even though the final result after you divide it by 2 is something that will fit into this int. That's why the code that we use is low, that will fit into int, plus high minus low over 2. So this way we're not creating this big value in between. We just calculate it in this way, and then we make sure that we don't get this integer overflow problem. I want to go through this algorithm thus one more time, just to make sure that you are happy with it, and that you are sure, make sure that since there are so many little things that you can get wrong, that you get that. So we start with this algorithm. The key is the input, the thing that we try to find. A is the array that we're looking for, the key into this array, and these are the current low and the current high that we have. So if we start the algorithm, of course, low would be 0 and high would be the length of the array, since then the interval that we're searching for is the full array. Now if high is less than low, then we haven't found the element, and so we return -1. Otherwise, you calculate the middle point of this array that is specified by a low, a high. Then we compare the middle point, the element at the middle, to the key. Now 3 things can happen. The key can either be larger than if you think of it in the case of strings, of course, larger mean that alphabetically it comes later, so it can be larger. And then it means that the lower point will stay the same, and we move this down. In fact, I think I might just have it wrong. If I make the higher point lower, I keep the low point the same, and I move the higher point. So this compare might probably return just what the exact opposite. So if it's less than, then I move the lower point upwards, and I get the high point stay the same. So in other words, it's this. I can either do this one or I do this one. As you can see, I've just made a little bit of a mistake by using this compare and interpreting incorrectly. So I'm one of those professional programmers that cannot implement binary search. Be careful, be warned. Make sure that you know what you're doing this. Otherwise, return. If it's not greater or less, then it must surely be equal. And then I return the point where I find it. So let's do an analysis of this algorithm. So in a sense, what we're doing is we make this array size that we have, we make it smaller every time. By doing this calculation, we halve it every time until we get to 1. And so if we know how many times we can do that, then clearly we know the running time of the algorithm. And this is, of course, an equivalent question as to ask how many times can you divide a number by 2 until you reach 1. Now, I mean, in a sense, this is exactly the same as this number of questions thing that I've asked. So how many times do I halve this interval until I get to where I find the number that I'm looking for? These are all the same kind of question that we ask, and of course we have proven for this case that it is log n times. Look there, we've proved it's log n times. So in this case, if you look at maybe at this tree over there, if it's 1, well, you do it just once, 2, it will take 2 steps. So you will see that this is indeed log n times. You don't have to half it exactly, since I mean it might be that the array is not completely a power of 2, then the array might be slightly skewed. There might be, if it's an uneven number, then one will be slightly bigger than the other, but in general that's not a problem. It will still be log n times. So having said that, I can re-ask the question. So if I have the same credit card company that needs to whitelist 10 million customers, processing 10,000 transactions per second, if they use binary search, what kind of computer is needed? And the answer, of course, in this case is any of those will work. Well, as I said the last time, a toaster might not be ideal, but definitely you could even do this on a cell phone of today, and you can solve this problem. So this concludes the story of the searching problem. And the moral of the story again, and will be the moral of the story for the rest of the semester, you should always be aware of the running time of your algorithm. Even though linear sounds good, if the problem size really grows, then linear might not even be good enough. Now, of course, it's not to say that if I found a linear algorithm, that for every linear algorithm there is a logarithmic algorithm. That's not the truth. But it is important to look at your algorithms, know what their running times are, analyze them, and see if we can find better algorithms in order to solve this problem. The other thing to take home is that by changing an algorithm from linear time to logarithmic time, we can do problems that would not have been possible at all. And then a final thing to take notice is that this binary search algorithm, you will find that in many kind of applications. So there's of course just the pure searching algorithm that we have, that's the one that I've implemented. There's this 20 question games that we've played. That's an application of the binary search algorithm. But you could also think of, if you have to find a function value of a function. There's an example in the textbook where you want to interpolate, in a sense, the function. You have maybe I should show this quickly for you. So you have this function, a monotonically increasing function, and I give you a y value, and then I ask you what's the corresponding x value over there. And you could indeed use also the binary search algorithm to find then this x value over there. So in other words, you find the inverse for, if I give you this, what was this x over there. And for this reason, some people would also refer to as the binary search algorithm as the bisection search algorithm. This is indeed a very nice example to read through in the textbook. I encourage you to read through this example. So this concludes then this video lecture. In the next one we will then discuss sorting.